It gives me great pleasure to talk here at the Birch Aquarium with such beautiful landscapes and seascapes here. And my interest in science is trying to understand the processes that shape planet Earth, okay? So here, what we're looking at is a map of the Earth. The elevations above sea level, topography, are shown in the warm colors, the mountain ranges in red. The elevations or depths below sea level, bathymetry, are shown in the blues, with the cooler being deeper, and the ridge crests stand out as prominent linear features on this map. The surface of the Earth, or the morphology, the relief, is what we're going to be talking about today, and what processes interact to control that. Landscape and seascape evolution, they record this complex interplay between tectonics, climate, erosion, and sediment supply. I don't want you leaving here today thinking that tectonics is the only process that controls morphology on planet Earth, but it leaves a dominant signature in the landscapes and seascapes, and we'll look at those today. Taper quarters of deformation. Stratigraphy. Stratigraphy on planet Earth is when sediments accumulate and form layers. When the sediment accumulates, it records some of the information at the time slice that it was being deposited. So we can look at stratigraphy in the past and use it to try to understand Earth history. Unfortunately, the book has many pages ripped out, and we have to be very clever at how we try to understand the plot of the story of Earth history. Morphology, again, this feature that we look at the relief on the Earth, both subaerially and submarine, but today's morphology, the surfaces you're looking at when buried, become tomorrow's stratigraphy. So what I'm trying to do is look at processes that shape the planet today to be a better investigator at looking at the geologic record to understand what happened in the past. Let's step back and talk a little bit about plate tectonic theory. What is the theory? The theory is that the outer shell of the Earth is rigid or strong, and it's made up of 12 large plates. These plates predominantly deform on their edges. These boundaries between plates come in three dominant styles. There's divergent plate boundaries where the plates are moving apart. These are seafloor ridges and rift basins. So these are areas where the plates are moving away from one another. There's convergent boundaries between these plates where they come together. If they're buoyant and continental crust, they deform and fold. In other areas, when it's oceanic lithosphere, it can be subducted and sinks back into the Earth and can be recycled. Other boundaries, translational boundaries, strike-slip faults and transform faults, the Earth slides by, these plates slide by one another without much extension or divergence or convergence. Now this is a very simplification of the plate tectonic theory, and we're going to look at some of the complexities today of these boundaries and how they don't operate always just in a simple mode. Let's just step back and talk a little bit about what happened with the plates over the last 225 million years. This gives us some perspective of the huge time frame that we're talking about when we look at geology. So here, in the Permian, the plates were all configured together in a large landmass called Pangaea. We had just destroyed the Proto-Atlantic. Iapetus had closed. We built mountain belts here where the plates came together, the continental plates here. And a plate, just to remind you, is made up of both continental and oceanic pieces. Plate boundaries do not follow the shoreline. So here, through time in the Triassic, about 200 million years ago, the plates started to separate into a northern piece, Laurasia, separated from Gondwanaland, the Tethys, by the Tethys Sea here, shown here. Continued movement and extension. Now these plates are moving at centimeters per year. A good way to think about it is they're moving at about the speed your fingernails grow. Okay, so through time this adds up. So here through the Cretaceous, we're just starting to form the Atlantic. And the Atlantic is forming as the Pacific is being consumed. Okay, so the Pacific is surrounded by these convergent margins, and we'll talk a little bit more about this. And finally, looking at our present day configuration of the continents. What's called a Wilson cycle is these continents move apart and back together on an order of about 500 million years. Okay, so slowly the Pacific Ocean will start to close and the plates will converge again. So here, we've talked a little bit about plates, translational boundaries sliding by one another, divergent boundaries where the plates move away from one another, and convergent boundaries where they move towards one another, either folding or one sinking beneath the other and being recycled into the Earth. Now when I talk about the lithosphere, or this outer shell, from the Greek, this means sphere of rock. This is the strong member of the outer shell of the Earth, and it floats on the asthenosphere, from the Greek meaning weak sphere or soft sphere. So the outer rind of the Earth, about 125 kilometers thick, is the strong carrying member of a lot of the deformation we're going to look at today. And this simple schematic just shows here at ridges, the lithosphere thins, the asthenosphere passively upwells, and it spreads apart on a conveyor belt. Here, because the Earth is not expanding, it has to be recycled and consumed, and this happens at these convergent or subduction zones. Let's look at this in a little more detail. I'd just like to go through a little bit and give you some idea about a cross-section of the Earth so the terminology is not overwhelming. The radius of the Earth is about 6,400 kilometers. We're looking at the upper 125 kilometers of the lithosphere, and it's made up of crustal material and upper mantle. So the lithosphere is defined slightly different than the crust. Crust is defined by seismic velocity. The lithosphere is defined by the ability to support a load or have strength. Today we're going to be talking mostly about the lithosphere, the upper crust, and lithospheric mantle. And it floats on this layer called the asthenosphere, which is softer. So at ridge crests, as I told you, we upwell asthenospheric material from depth. It melts due to decompression and forms new crust, and this crust locks in the magnetic signal at the time it's formed. The Earth's magnetic field has flipped polarity, and these flips are recorded in the seafloor, so we get a record of how the seafloor is spreading and the rate at which it's spreading. So the magnetic signal allows us to put some constraints on the age of the seafloor as well as the rate of spreading. And this here is just bathymetry, the hot colors being roughly about 2,500 meters depth, and the cooler colors going out to about 3,500, 4,000 meters. And this just shows a segment of the mid-ocean ridge in the Pacific at 9 degrees north, and you can actually see some complexities and overlapping of the ridge here. So this is a divergent type boundary. We also have divergence on land and continental regimes. This here is the Basin and Range. This is the Great Valley here, California. And this topography here, which is blown up here, you can see highs and lows, mostly all through Nevada. This is caused by the Earth stretching. And the lithosphere and continents, you can think of it much like a Milky Way bar, with the outer crust being the chocolate, and it breaks in discrete cracks and chunks. And deeper in the lithosphere, where it's warm, it extends more uniformly like the taffy. So here you're looking at the outer chocolate breaking in discrete chunks, and what happens is you form these horse or high standing blocks and these grobens, which are low standing blocks, and they're bounded by normal faults where the displacement is down, and you can see the layers. So this gives rise to the highs and lows that we see in the Basin and Range. So we have divergence also in continents as well as in ocean lithosphere. This here shows the San Andreas Fault translational boundary here. We have also a translational boundary between ridge crest segments where the plates slide by one another without much deformation. I've just put this picture up here to show that how the San Andreas evolved through time from 30 million years ago to present. Everything seems to first happen at LA. We first subducted the ridge crest here in the subduction zone, and this is the Farallon plate being subducted beneath the North American plate. And as we subducted the ridge, we transformed this boundary between the Pacific Plate and the North American Plate into a right lateral strike-slip fault. And I'll talk in detail about what a right lateral strike-slip fault is further on. This continued to grow as we continued to subduct the ridge system till we got to the present day configuration. So this is one of these translational boundaries where one plate is sliding by another. Convergent boundaries. Here, again, just to point out, we have oceanic crust. It's thinner than continental crust. And here's the lithosphere, which is both the crust and the upper mantle. Here we have oceanic crust being subducted and recycled beneath continental crust. In this image, we can also have oceanic crust being subducted and recycled beneath oceanic lithosphere. So here we can form island arcs. This is much like the Aleutians. Here, this is like the Andes or Cascadia, where we subduct oceanic lithosphere beneath continental. And the ring of fire, there's volcanism associated with this subduction as the plate dewaters, and this water helps melt some of the overriding plate. And what we get is volcanism at a certain distance away from the trench or where the plate's being subducted. And this leads to a ring of fire or volcanism, which most of you are familiar with in the Pacific, because the Pacific is dominantly bounded by these convergent type margins. We also have convergence on the continents. Although the continental crust, being more buoyant, doesn't like to be subducted or recycled down into the mantle, and it gives rise to some of the highest elevations we see in planet Earth here in the Himalayas and Tibetan Plateau. What happens is India collides into the Eurasian plate. We fold and deform the continental crust, we thicken it, and give rise to some of this high elevation. Okay? So there's many styles of these types of plate boundaries. I'd like to digress for a moment and just let you see how this evolved. In the 1800s, Wagner made the observations that you could take the continents like jigsaw pieces and put them back together. He thought that the plates were once all back together like Pangea. But he proposed the mechanism was that the continents plowed through the oceanic lithosphere. And this wasn't well accepted because the forces required for the continents to plow through the oceanic lithosphere is extremely high. So the theoreticians weren't really willing to accept this idea of continental drift, despite the robustness of the observations. Well, down the road, Harry Hess and other researchers at Lamont, Scripps, Woods Hole started compiling lots of information about the bottom of the ocean. And even today, we have better maps of Mars than we do of the bottom of the ocean. So you can understand it took till 1960 for the theory of plate tectonics to really take hold. But Harry Hess made some incredible observations, and what he said is the seafloor is spreading. The plates are made up of oceanic and continental lithosphere, and they move apart from spreading ridges and are consumed or recycled at subduction zones. So it was the theory that went around with the observation that allowed this concept to be accepted. This here is an elevation map of California. I'm going to walk us through three areas today: the Eel Basin, Lake Tahoe, and La Jolla. And from north to south, these represent convergent type margin, an extensional type plate system, and a translational type plate system. So the deformation that we observe on planet Earth, most of it is manifested in our state. Just to locate you so you can see the relationship between the major faults and the topography in California, here we see the Garlock Fault coming across. We have the transverse range here, LA. We have the Mojave Desert, the Great Valley here, the Sierra Nevadas, Lake Tahoe. So we move up San Francisco Bay, we have the San Andreas Fault System coming all the way up to this triple junction up at Mendocino, up by Humboldt, Northern California. And we'll look at this in more detail of how the deformation has occurred there. So the Eel Basin. The Eel Basin is sitting right landward of this subduction zone that's shown here by the hatchered symbol. We have the Mendocino fracture zone. This is a transform boundary between the ridge and here the San Andreas Fault coming up from the south. So we have a triple junction right here. And what I'd really like you to take out of this figure is that the Gorda Plate is being subducted beneath the North American Plate, but the Pacific Plate is moving northward with respect to the Gorda Plate and North American Plate. And so what happens is we cause deformation in this corner of the plate and folding. This here is a topographic image with the whites being roughly 2,000 meters, the elevation of the mountain ranges here in Northern California, and this green color being close to sea level. When you have these plates interacting, it's much like folding up a rug. We get these highs, which are called anticlines. We get these lows, which are called synclines. Okay, so we're folding up the rug, or the lithosphere here, and you can actually see that the trend, the structural trend, starts rotating counterclockwise as we come close to the Cape Mendocino Triple Junction. And this is in response to the compression induced by the northward movement of the Pacific Plate. These folds play an important role in the sediment dispersal and sediment preservation on the California margin. The rivers are locked in the lows, okay? And in between them are drainage divides, which are these highs. So the rivers, the Mad River, the Klamath River, the Eel River, flow in the lows in this folded up carpet and control where we put sediment into the basin. This is in 1995. The Eel River delivers more sediment than any other river in the contiguous United States. This is at flood stage at 1995 on the plume, and you can see here that the Eel River is bounded by topographic highs both to the south and to the north. And this is the large plume that's escaping during flood stage. How am I going to show you some of the data? So let's just look at data acquisition and the types of data that I'm going to show you today so you'll understand what we're looking at. Basically, we have one of the best technology and groups looking at seafloor and subsurface stratigraphy. Scripps has built a critical mass of investigators that are looking at these problems, and I think it's one of the best in the world. What we have is we have swath bathymetry capability that allows us to make beautiful images that can tell us about process and seascapes on the seafloor with resolution that's been unprecedented until now. So we're getting down to the resolution of the scale of the process we're interested in studying. And that's important if you're trying to understand how things formed in response to these forcing functions. So we make images of the seafloor. We also have new tools that allow us to look at the layers beneath the seafloor. So today's seafloor is going to be tomorrow's stratigraphic horizon. So we have new tools that allow us to penetrate the seafloor and look at the sub-bottom record to try to understand some Earth history. We also have side-scan towed vehicles that allow us to look at the roughness of this surface. So we can look at the surface itself, we can look beneath the surface like a road cut, and we can also look at the roughness of the surface. Just to show you some of the sub-bottom here, the system that we've been using, we've developed this in conjunction with EdgeTech, a corporation, and another university, Florida Atlantic University. And this shows data collected on coincident lines off South Carolina. And this is our SubBottom imagery. This is meters below sub-bottom, and this is roughly on the scale of about 100 meters. And you're looking at features in the geologic record, much like you'd look at a roadside cut as you drove by. And even non-experts, it's readily apparent that the resolution of the features we're seeing much better than off-the-shelf tools that do not image the sub-bottom so well. So we're in a stage of technology that we can start to argue about what forms these surfaces instead of trying to guess what are the surfaces. Let's go back to the Eel River now and some of the data we've collected. So here I'm showing you offshore swath bathymetry. This is the seafloor, and the onshore mountain ranges and drainage systems. Now remember, I told you that the Eel River, and I showed you onshore, it's folded up like a rug. Well, we can see that offshore, out on the slope, a large distance from the margin, we can see what is this little Salmon Anticline. But during the course of this study, a stratiform study funded by the Office of Naval Research, we weren't confident in how this fault system connected back up on land, whether it connected to this high, the Table Bluff, or this high in the middle of Humboldt Bay, which is shown here in Eureka, California. So we weren't able to see beneath the sands on the inner shelf to understand the continuity or how these faults connected, or is this one whole fault system, and how it affected sediment dispersal. With our new system, we were able for the first time to see beneath this veneer of sand. So over here, this is meters below the seafloor. There's the seafloor there. What you can see is that there's these layers that are dipping, and this is 200 meters here to give you some scale, and they're actually folded. So here is the top of the fold, or anticline, and you can actually see it go back down the other side, and here's the fault. And these are different lines that are roughly 200 meters apart, and you can notice that the geometry of the subsurface changes markedly. Geology is very complex, and it's spatially varying. Down here in the bottom line, you can actually see the fault trace, okay? So with this new instrument, we were able to connect some of the offshore features through the shallow water regions where it's very difficult to image the subsurface onto the onshore regions and try to understand them. As we move away from this fault, what we notice, so here's the little Salmon Anticline with a thin veneer of modern sediment on top. As we move south towards the Eel River, or Eel Syncline, a low in this fold, we start accumulating large amounts of sediment. So over here, we're accumulating only a few meters, and then the same time slice, we're accumulating over 20 meters here. And it continues to thicken to about 40 meters. Now this deformation or folding is long-lived. This here is 40 meters. Can't see the scale here, but this scale, so from here to the bottom of the picture here, is on the order of about 3 kilometers. So it shows that the same fold or syncline in the multi-channel seismic line persists and is long-lived. So this is a receptacle for sediment. Well, why is this important? Well, the Eel margin, when I've surveyed there for 3 years, only one day did I see the shoreline, even though I was only a few hundred meters offshore because it's foggy and raining all the time. Weather that's great if you're a redwood, but not a scientist. So these mountainous coastal regions get large rainfall. Being close to the Mendocino Triple Junction, it has many earthquakes. What this does is this causes landslides. And just an example, this is from December 1999 after torrential rainfall in northern Venezuela, just north of Caracas. The light shows areas that are denuded and stripped, harvested of the soils and standing vegetation. And this vegetation is very efficiently funneled out to the ocean because there's no trapping mechanism in these short rivers that are close to the sea. So here, these actively deforming margins with coastal mountains might be important harvesters of standing terrigenous carbon and might funnel them efficiently out to the ocean where they're rapidly buried and preserved. We're trying to understand the importance of these in a global CO2, a carbon cycle, and try to determine if this is important. Maybe I'll come back next year and tell you if we believe this is an important contributor. Right now, we just don't know. Okay, now let's jump to Lake Tahoe. Okay, Lake Tahoe is situated, this is the Sierra Mountains, this is the Basin and Range that I talked to you about. Lake Tahoe is situated right in the boundary of the stable Sierra batholith and the extending Basin and Range. North being up to the top of the screen, just some areas for those familiar with Lake Tahoe to give you some reference frame. Here there's 3 major faults that carve Lake Tahoe: the Incline Fault, the State Line Fault, and the Dollar Point West Tahoe Fault. Now these faults are predominantly normal faults, and they dip to the east. So here, what we have is the fault systems on any one of these faults, the footwall shown here in brown, the hanging wall shown here in green. We have a fault dipping to the east, with the eastern side being downplaced, and we have sediment and water in the area of thinning and extension where we make a basin or a hole. Okay? So this here on the western side is the footwall, and then on the eastern side is the hanging wall. And just imagine that we have 3 of these faults, not just a simple picture shown here. When we combine this with the new data of Lake Tahoe, a lot of things start to emerge. First thing I'd like to draw your attention to is the McKinney slide. These blocks across the lake here is on the order of about 15 kilometers. These blocks are up in range to 1 kilometer in size. We believe they were vacated by a large landslide in McKinney Bay that failed and fed these large blocks to the deep part of Lake Tahoe. The deepest part of Lake Tahoe is about 500 meters deep. The purple color shown here. So that's one thing I'd like you to look at here, is that we had a large failure. This is the scar, and the material that used to be here on the western shore of Lake Tahoe is now distributed in the lake. This must have been a violent event. And if you were a homeowner or someone on the lake, I don't think you'd want to be there. What we're trying to understand in our research is the age. When did this happen? And what were some of the triggering mechanisms that allowed this to happen? The second thing that I'd like to point out, and I'm going to show you some data, is the Dollar Point fault shown here, or excuse me, the State Line fault. The scarp here is shown very well, but you can see it wind its way down and its sinuous shape, and I'm going to show you seismic profiles across here. I'm also going to show you the eastern shoreline, where this reddish color is an old lake level horizon, a paleo shoreline, and this magenta color is new sediment that are building out in response to drainage into the lake today. What's really fascinating is the amount of uplift. So this is the footwall, it's up. This side is the hanging wall, so it's down. The amount of displacement across some of these faults is consistent with the depth difference we see from the eastern side of this paleo lake surface to where we see comparable paleo lake surfaces here. So on the western side, on the footwall, they're on the order of about 10 to 15 meters shallower than they are on the eastern side due to this deformation. And this is the same kind of relief we're going to see across the State Line fault. Okay, here's one of our chirp seismic sections across the State Line fault. Here's meters beneath the vehicle. So here you're seeing the depth of the lake being on the order of about 500 meters. Scale here 100 meters. This is the lake floor. The McKinney Bay slide, which is associated with those big blocks, shows up in seismic profiles as this nondescript, lacking reflectors, acoustic character in seismics. So you can see it here, and it's offset over here. And the offset is on the order of about 20 meters, where the offset of the seafloor is only on the order of about 10 meters. You can notice that on the hanging wall side, we've collected much more sediment than we have on the footwall side. So there's been preferential accumulation on the hanging wall side by these gravity flows going down into the lake than there are up on the footwall because it's slightly higher. So this shows a consistent offset with what we see on some of these paleo shorelines. And what we're trying to understand, our group is trying to understand, is how often do these faults happen in the past? What's the recurrence interval? And should we be bracing ourselves for a fault in the near future, or is it far off? This here is a blow-up of the eastern side of the lake. Here's the old paleo shoreline. Here's the prograding sediment in response to the drainage system supplying modern-day sediment out to the lake. And we were just up in Lake Tahoe last week with a rig trying to core through this surface. This is 7.5 meters for scale, 30 meters. This is this buried erosive surface, and it outcrops and is at the lake floor here. And you'd say, well, why don't you just core here and get the sediment where it outcrops? It's much easier. We brought this expensive rig and to core over here and get 10-meter cores through the surface. And the reason is, we want to get the youngest material beneath this surface, okay, and the oldest material above this surface to create an accurate date or minimize the hiatus associated with this surface. Over here, all the time that's represented by this slug of sediment here is missing here. so our age constraints would be poor. Okay? So we were unsuccessful. We got about an 8-meter core, which I don't believe penetrated the surface. We had a storm move into Lake Tahoe with 40-mile-an-hour winds, and we came out here with a barge powered by this little power boat, and we had a 20-ton crane lowering this 30-foot monster over the side. And here we penetrated, the barrel penetrated 10 meters, but only recovered about a half a meter of sediment. It'll give us some insights, but I don't think we successfully cored the surface that we needed to get to understand the timing of these lake levels and put some constraints on the rate at which the relief is growing. I'm now going to show you a little movie of Lake Tahoe where you can get some feeling of the blocks and some of the features that I've just talked about. We're going to be coming in from the south. We'll go up to the north along the state line fault, the state line fault being right here, which you just saw a profile across. You can see the slide scar of the McKinney Bay. Look at that block. It looks like it's not long for this earth there. Here, we're now going down the incline fault. Look at the size of these blocks. Just amazing. This is the debris field associated with that slide. Now we're coming, Heavenly Valley ski area was off to the left. We're coming Emerald Bay. We're swinging back up along the California margin. There's the slide scar where all these debris field blocks came from. Now we're going to go right up this slide scar, and we're going to exit out the only exit river of Lake Tahoe, the Truckee River. And the Truckee River plays an important role in lake levels, is what our group believes. Okay, let's now move down to La Jolla and talk a little bit about translational margins. Here, this is the aerial view that's shown there. These canyons and the confluence of them appear to have a tectonic control. And you can actually see on the beach the color of the sand changes just to the south of the beach and tennis club. This is where the fault emerges. Okay, so the Rose Canyon, Mount Soledad, and Country Club Fault wrap around here, right along this part. So here's the shoreline. Here's the beach and tennis club. These faults come along and take a jog to the west and then emerge offshore. And we're going to look at some of the geology here, but the only Cretaceous in this area, Cretaceous being older than 65 million years ago, it's a mudstone, darker colored, has more fossils. This is only exposed here in the cove, and as you go northward towards Scripps, it's predominantly Eocene and associated with the large submarine fan complex. Okay. So what's happening with Mount Soledad? Why do we have Cretaceous sediment here and younger sediment to the north? A right lateral fault. A right lateral fault, the fault plane shown in magenta, vertical, with a piercing point, like your fence, your patio. So here, this piercing point crosses the fault. We have an earthquake, and we displace this piercing point. So if you stand on this plate and stand where the piercing point is and look where it is across the fault, it's to your right. The same would hold true if you stood on the other plate and looked to where the other piercing point is. It's to your right. Okay, so this is a right lateral fault. Well, faults aren't straight. Faults have jogs and kinks in them, and this gives rise to some of the uplift and subsidence we see along the California margin. This here is a right lateral fault, like I showed you last time, with a left jog. Okay? So in this area, as this plate to the left slides by this portion of the plate to the right, we get here compression. We fold up, we have a space problem. Now, which side of the plate goes up depends on the structure of this fault and the dip of the fault. Okay? So Mount Soledad is going up. We know that the Rose Canyon predominantly dips to the east, and this area is going up. The Rose Canyon has slip on it up to rates of 1.5 millimeters per year. Okay? It has been trenched on shore, and it's been active in the last 10,000 years. So here, Mount Soledad is going up, and it's going up at a rate of about 12 inches per 1,000 years, maybe a little more. Conversely, on a right lateral fault, if it takes a right lateral jog, we make extension or form a basin. We have a space problem and we lose volume of material and we make a hole. Okay, so this is here from Pat Abbott's book, just showing the uplift of Mount Soledad and the exposure of some of these mudstones that we see here. We've made a little movie. This is thanks to people in my lab, J.P. Walsh, and others in the lab, Wilson Long, who spent long hours merging this digital mosaic with a elevation model. And so now what we're going to do is we're going to look at the relief generated. So the fault's coming right out here. Here's Mount Soledad, and you can see the uplift and height of Mount Soledad above the surrounding region. We'll back out here. This is the first time I've gone down Ardath Road and not seen traffic. So here, we're coming down into Jolla Cove. There's the beach and tennis club. We're swinging around. Oh, he went through the mountain. He hurt me there. But, and we're swinging back around. So you can see that the influence and compression, Mount Soledad has uplifted this area and exposed the deeper layers. And that's why we have this abrupt boundary or contact between the Cretaceous and Eocene. We've also been doing a lot of work offshore, and this fault continues. Here's La Jolla Cove to register you. Here, continuing offshore. I'm going to show you some data here where the fault actually takes a right lateral jog and makes a basin. Again, some chirp data. So what we're going to notice here is the scale here, meters. So each of these is 10 meters. This is 200 meters. One of the faults is coming, so this is cutting across the margin from shallow to deep. And one of the faults is coming in and then stepping across to this other fault or taking a jog, and we're making a hole. And this hole is filled up by diverging sediment. And what we want to do is we want to drill this sediment. It's about 40 meters deep. We'll need a special rig to drill this. But for the first time, if we can acquire this surface and date it, we can put some constraints on the onset of the Rose Canyon fault. Another benefit is that here, coming off of this knob here, is a Miocene basaltic dike. And what we're going to do is map how this comes across. We can see it here. You can see it outcrop here if you come up closer. And it comes across, and we're wondering if it intersects this strike-slip fault, and we can look for it on the other side, and this will provide that piercing point or fence that we can actually get displacement. So we're hopeful that we'll be able to get timing and displacement, which will give us rate and some information on the Rose Canyon fault. That was done in April. In May, we went out with the Atlantis, and we mapped the deeper portions of the canyon. Here's La Jolla Cove. You can see the canyon here. It's very sinuous. It displays many characteristics similar to a fluvial system or river system that you'd see on land. It has meanders, meander cutoffs. It has very similar characteristics. Let me just show you a different perspective of this image. We're now looking down the canyon with warm colors being shallow, cool colors being deep, and you can actually see this sinuous shape, these cutoffs here associated with the canyon that appears to have some structural control. What I'd like to draw your attention to is these areas that look, you can see them delineated here and here, that look like they're downdropped right on the axis of this canyon. Let's take a different perspective of this. So now we're looking from offshore to onshore, and you can see these blocks imaged well. We need to collect some sub-bottom data across these blocks because there's two options. One, these blocks are rotational slump blocks that are starting to fail because the canyon downcut and oversteepened the walls and undermined the toes of these blocks so they can start to slide. Okay? The other option is that the canyon, when it was younger and eroding, was wider up here, the flow, and so it eroded wider areas like it might have here. So we need to go and look at the subsurface layering to discern between these two models. But if these are blocks and we have an earthquake, or we have like large storminess like associated with El Nino, and these blocks fail, they could generate a tsunami that would be focused right up this area, and guess whose offices are right in here? It'd be a bad day. I'd like to leave you, as I told you in the beginning and wrapping up here, is that landscapes and seascapes are not, say that 10 times quick, are not only controlled by tectonics. Tectonics leaves a large fingerprint. It's a robust signal. But other processes shape landscapes and seascapes. And yesterday, my lab took the freedom to melt all the ice in the northern hemisphere. And this shows what La Jolla would look like with a 5-meter sea level rise. So climate, glaciers, pluvial, rainy season, aridity, all of these affect landscapes and seascapes. So this is what it would look like if we melted all the ice in the northern hemisphere. Well, what would it look like if we removed Antarctica? So there's La Jolla when we remove and melt Antarctica, which is about 60 meters equivalent sea level rise. So this shows you that we'd now have a golf course on the ocean. A lot of La Jolla, the sea cliffs would just be topped by sea level. So this here is a large change, but we're much better off than a large portion of the country. On the east coast, a 60-meter rise. The Piedmont on the Appalachians would be the shoreline. In the interior part, Denver would be becoming a much more popular place to live. So with that, I'd like to thank you for your attention. We're going to be mapping this fall, November. We're going to be doing the same map and continuing some of the data density that we have offshore, onshore. And if any of you'd like to come with us, we have available spaces for day trips to come out and map the ocean floor with us, and would welcome your participation. Thank you. There is gas that actually is migrating right out of the seafloor. We know this from cores, gas taken cores, and sniffers that detect chemicals associated with the expulsion of fluids. The oil companies in Humboldt, one of the largest gas producing wells is right on shore there on the Anticline. But because of the restrictions in California's laws for offshore exploration and drilling, the profile I showed you in the bottom there, the MCS, was donated by an oil company because they've pretty much given up doing exploration here for the time being. I don't know how that's going to evolve in the future, but the laws for offshore drilling and exploration are pretty tough. So there's a lot of potential for gas and hydrocarbons, just for the reasons I said, is that you get the synclines full of sediment, and then the hydrocarbons, because they're buoyant, migrate up dip to the anticlines. Absolutely. Sea level falls due to glaciation and taking water and evaporating it from the oceans and storing it on land as ice sheets is equivalent to about 125 meters. Where I showed you was 400 meters and deeper. So what seems to happen is the upper reaches of these canyon systems where they're exposed, or steeper parts of the margin, what happens is the sediment in the water is denser than the ambient sediment. So it forms a density flow. And these density flows abrade and carve and sculpture. So they have many similarities to a fluvial system. In a fluvial system, if you have water and air, in this system, the density contrast is much less. You have sediment-laden water in water. Okay? But it was formed in the submarine environment. Yes, there could be river systems on the upper levels, but the data I showed you was 400 meters below the sea surface today. And these rivers, when they dump out, and work that we've done, they create these density flows called hyperpycnal flows. And these flows have the ability to erode and scour. So yes, there's fluvial systems on the inshore part, but when we're out here, it's in the marine environment. okay, and the water depths that here that I showed you. Okay, we're situated, we're deeper than like 400 meters in this area, and sea level didn't expose this part of the shelf. Well, San Diego's been uplifting about 5 to 12 inches per 1,000 years. And so what we have is, in fact, these terraces are being uplifted and brought and elevated. So tectonics is creating a relative sea level change. Sea level from the Cretaceous about 100 million years ago was at its highest globally and has been falling. But tectonic activity can make the land emerge. Okay.
Living on La Jolla Boulevard, I want to know.
I wouldn't be worried at all. I mainly put those figures in there to give you some concept of the elevation that we have in this area and the uplift that's been associated with Mount Soledad. Global warming, we do seem to be going into a warm period. It's not my expertise. The warming seems to be accentuated at the poles. What's going to happen? We're conducting a huge experiment in planet Earth, and the only difference with this and what I do daily is we're part of the experiment. So I don't know. It must be a very big drain. I was asked, a man put drains in his house along the shore, each room, in case of a tsunami. A tsunami, the problem with tsunamis is that in deep water, they're very small waves. And as they shoal, they become very large, and they travel at highway speeds in shallow water. They travel at jet speeds in the deep water and highway speeds in shallow water. So unless his drain had a great pump, and it's the force, the impact. So he might drain well afterwards if he survives the hit. I think it would be a good place. These faults are deep, okay? They're crustal structure faults, so they go deep into the earth. They're not shallow. Where they breach on the surface might not be coincident with where they're deeper, because faults are complicated zones. Right in this area, in fact, you'll see, to say it's a fault or a single lineament is not accurate. It's a deformed area. And right now, the Mount Soledad fault is the most active, with Rose Canyon and Country Club being subordinate. But these faults are deep-seated structures, so if you're going to plant a palm tree, I'm happy to come help. To answer your question, I might just leap back to we've looked at rift basin or pulling apart. What makes a continent pull apart? And it looks like the Basin and Range right now in Nevada, between the Colorado Plateau and the Sierra Batholith, is actually pulling apart. Okay? And what makes this happen, and what makes it successful to break all the way to an ocean? We don't know. The strength of the lithosphere when it's cold exceeds any forces that are associated with a ridge push by gravitational forces, because ridges are high and they have a gravitational force pushing on them, or slab pull, when these subduction zones and these cold, dense slabs stick into the interior of the earth, they pull things. These forces are the predominant plate pushing forces, and they're not high enough to break old, cold lithosphere. So the gravitational forces we don't think is enough. We think, our group thinks that it's far field forces that act pulling on the plate, in addition to having something that softens the plate, such as the introduction of heat. So we don't think you could break old, cold lithosphere. We think that you have to have a few things come together that facilitates this deformation.
If the Pacific plate is diving under the North American plate, my naive mind, that would seem to me to imply compression, not pulling apart.
That's a very good, and right? And what we see in a lot of convergent margins is we see what's called back arc extension. So even though we have subduction going on here, which you would think would induce compression in this plate, think of this. This is one of the explanations that has been put forward to try to explain this so-called paradox, that you'd think you'd put the plate, this plate, in compression when this plate went back. One is what happened, the asthenosphere flow takes this plate, which is sticking far down in it, and pushes it back like the asthenosphere has a wind. So it pushes this plate back. So even though the plate's going back, the coupling with this overriding plate might not be so large. The second thing is it's all relative. These plates coming together, the plates could be moving like this, but this plate moving faster. In that scenario, when the plates seem to be moving in the same relative direction, but this one, my right hand, moving faster, and that way you get relative convergence, that's one of the ideas that allows this plate to extend because it's still moving itself. It's just on its boundary, it's experiencing this local relative convergence. So, but it's a very good question, and I don't want to let you think that we know all the answers. Back arc extension and extension in these areas that have subduction on their boundary is an ongoing research area.
Well, I'm sure Neil will be glad to talk to any of you who have further questions, but thank you very much, Neil. It's great to have you.
Thank you.